Hello guys, welcome to this video and we're gonna continue using our laptop. So we I'm gonna go just give you a quick recap what we have done. So this is the slide we have done in the previous video. So we are understanding score matching. So we first of all understand this type of network and we want to do score matching. So we're gonna go estimating this grad with respect to x ln of log of not ln of just log of p of x. So we are focusing on to learning this using neural network as theta. So our goal is to find this using our neural network which has a parameter theta, and this is actually a vector valued vector valued function. So and and we see this is the just I'm gonna just giving a quick recap. So this is actually the bimodal bimodal distribution which has this two mode here and here, and this is we are just so this arrow is just pointing towards this. If this is, I think if you are just going there, so if this is, so if you this is saying this arrow is pointing towards this mode, so you can see here, and this arrow also pointing toward this mode. So these are this arrow, this vector field as of theta or ln, so grad ln of x ln of px, px is equal to this as theta. So this actually gives the direction of where our data lies. So if we so we understand why we use score function, because we can just get rid out of the normalization constant, and we understand this. First of all, we understand the score matching, and we see that the computation of this if we do integration by part, we get this trace of Jacobian, which is computationally expensive to calculate. Then later on that, then we see that how to this is the trace of Jacobian. So this is the trace of Jacobian. So if we calculate this Jacobian of this diagonal, this is the trace of Jacobian. If you just get just sum of this diagonal element of this derivative, we get this quantity, the trace of Jacobian. So if our dimension increases, this trace of Jacobian's calculation will be extremely computationally expensive, and we understand this is in denoising score matching, which is given by Vincent, and we see that we first of all we take the data as we actually apply this kernel transition kernel which takes x which takes x, and this kernel just gives this x tilde, and we get the data from this distribution. And if you do score matching here, so noise bit drop, so score of the noise bit drop, this is the score of this function of the noise bit drop distributions. And if you solve this, we can get rid of this quantity, and we have this quantity which is the q sigma of this kernel. We can, this is just a Gaussian kernel, we can easily calculate this in a closed form. So if you go there, so it is scalable for high dimensional data and denoising tasks. From a score approximation, we can just reduce into denoising tasks. So we can just move on here. So and after that, we look at uh, denoiser, why how it is called denoiser, and understand another technique of slice score matching. So it's just a projection. So we will gonna go do some projection onto some straight line, and this is a projection, this formula of projection, this dot product between this quantity and this quantity, this quantity. If this is if the vector fields are same, this quantity will be same, and our loss will be minimum. And if we do so we doesn't have to just if you just look at here involve the Jacobian calculation. So this is called and we doesn't have to calculate the Jacobians. So just we have to calculate the uh, Jacobian vector product, which is actually a directional derivatives which can be computed easily with a backpropagation. So I think this is scalable because it's, the calculations just we can just do you can see here the calculations. So this is just one step calculation. I've already covered this calculations in the previous video. So one backpropagation is sufficient and slightly slower than denoising skew matching. So we also understand the algorithm of this skew matching. Then we see sampling from this. If we do some, so we do we estimate this as theta using slice skew matching or denoising skew matching. So denoising, whatever we do, if we if you do slice skew matching or denoising skew matching and we are able to approximate this quantity as a theta, then after that we can employ Langevin sampling to sample the data from the desired distribution P of X. And if I see you here, so if we are just following the noisy score. We are following the noisy gradient. So if I see here, so this is what this actually does not give the desired results as we are looking for. If I see you here, so if you apply the Langevin sampling, and if I see you, so results, if I see the results are not satisfying factory because we are just naively apply this Langevin sampling process. So there are some pitfalls we are just looking on. So if I can, I will gonna use the sliders in from this Yan song slide. So you can also, so I'm gonna using this slide to explain you. So as I mentioned, there is some. So as I mentioned you, so lack of samples in the low data density regions. So what does it actually mean? So if I show you, so this is our data distribution. You can see here, this is our data density and which has this two mode you can see here. And there are two modes. And if we just, this is the original score of a model. So this is the original score of a model, and eh, the vector arrows are pointing towards the pointing towards the mode of the data distribution. So you can see here, so this is uh, actual vector field and this is the estimated score. So you can see here we have same. There is the vectors are pointing toward this. Here is correct and here is correct, but you can see here there is wrong. There is estimated score is not accurate at this region. Uh, the vector fields are accurate at this region. Or where we have a data sample. So this is we have IID sample. So means we have some in our data set we have samples. So you can see here there is correctness, there is correctness here, but the vector field around here and yours are not accurate. So there is some. So we doesn't have a samples here. So we have a samples here. So our vector fields are good. Our fields are good here, but we doesn't have a sample here. So we have to deal with the problem. So how can so as I'm saying, so this is accurate because we have the samples, some samples in our dataset which is from here and from here. So so our score, because we for the estimation of the score we use samples from our dataset which lie within this region. So what the score outside is absolutely inaccurate from this. So we doesn't have a sample here, so our density estimation will be wrong. So our vector field estimation will be wrong here. So Langevin sampling will have a trouble in exploring the low density region. So if you initialize the particle all over the space, then if we start running this Langevin sampling for enough, it will not converge as easily. So if we start from here and if Langevin sampling start exploring the region, it will have a very trouble in exploring this region. So it will have a trouble. So if you initialize the particle all over this place and we we then say that let's explore the region. So Langevin sampling will doesn't have a good gradients to convert towards this region. So if this started from here, if this started from here, it will go around here, and it is started from here, it will go around here. But there is accuracy only in these regions. So so how can you solve this problem? So square estimation. So to solve the problem with square estimation, we're gonna use Gaussian perturbation. Means we're gonna add Gaussian noise to our data set. So our what we're gonna do is we're gonna go take the sample of dog and cat and dog, and then we're gonna go add Gaussian noise to it, and our sample will just spread all over this space because so I'm gonna show you. So that's it. So this is the sample around here, and this is sample around here, these regions. And if we add more and more noise, it will just cover all over this space and our density. And we have a sample of here and all over. We have samples all over this space. So we have sample here and here at the first, but if you add enough noise to the image, so this image will probably lie. This image is probably lie between these regions. And if you add even more noise, it will just cover all the regions, and we have samples all from all the regions, and our score estimation will be accurate, but our density will be this, not the actual one, not this. Our density will be this, but not our density will not be this. So So this is accurate. This is the original Petrov score, and this is the estimated score using our. We're gonna estimate using some neural networks. So vector field neural network. So it will gonna go estimated. So high noise provide useful directional information for the Langevin sampling. So if this particle is started from here, it will can go from here to here, or or if we started from here, it can also converge towards here towards this region also. There are some accuracy now. So but we are not actually approximating the real density right now, so we are approximating the Petrov data density. So as I'm saying, we're gonna go add noise and our samples will be all over the space. But and I'm also saying that Petrov distribution is no longer approximate the true data density. So we are actually making a trade-off between the data density and score accuracy. So if we add more noise, our score estimation will be good, but our obtained density function will be Petrov density, which is this like this images show. And so so rather than using just a single noise, we're gonna go use the increasing level of noise, as you can see here. So from many noise levels. So in practice we can use thousands also, but I'm just giving three right now. So this is your original, this is your samples. Like you can, this is the image of cat and this is the image of dog, and if you add more noise, your samples will be spread all over the space, as you can see. So our score estimation there will be correct. So in these regions we have a sample. So in these regions our score estimation will be good, and in this region our score estimation will be good. And if we add more and more noise, our samples will spread all around the space, and our score estimation around all the space will be accurate. So this is why we add noise. Uh, so we are using multiple scale of noise, and you understand why we are using this. So our density become like this. This is a P sigma 1, P sigma 2, P sigma 3. So we have different density right now. This is so if we sample from there, so if we sample from there, we'll get the sample from this P sigma 3 distribution, not by P sigma x. P max. So we are no longer estimating the px, we are approximating the p sigma 3 right now. So we're gonna go make our data like this. So many samples we're gonna go add noise. So this will reach all over this space. So this is the score. This is the score. This is the score. This is the so it has different score. So every density have different score, as I'm saying here, showing here. So we can have we can have for this p sigma 1 we can have one single network, and for p sigma 2 we can have different network, and p sigma 3 we have different network. But the but what we're doing is we are, rather than creating a separate sampler like this, rather than just approximating the simple single this network, we are making this as a noise conditional. We are using some computational tricks here to also incorporate noise. So to also incorporate noise, and I will explain this formula later on. So so imagine, so this is so we have this all this sampler. So you can just see we have all this we have the score of this, we have the score of this thing, and we have the score of these things, and using this score we're gonna go 10 samples. So in this, so we just initialize the particle in this the square function of this density. So because the square is accurate, so it will give good directional, this vector field will give the good directional informations. And if you run this enough, the particle will move closer towards this. So and particle will move towards the good region, because the score is right now right. But score is right, but sample quality is not good. So score is so our samples will go towards the good region because the directional information is right, because the score is right here. And we just take it this from here to here, from here to I paste it here, and then I just even run the sampling. If I even run the sampling, so it will go towards the gooder region. So and I just taking it here, and I'm just even running. So our samples will lies here. So so we are actually our so we are having two benefits. So first of all, our Langevin sampling, this score is accurate, this score is accurate. Our Langevin sampling doesn't have a trouble to approach towards this density, and we are decreasing the level of noise, and we are actually going to the sigma 1, which have the least amount of noise. So our if we take the sample from this score function, we're gonna get good sample. And this score function is actually take this sigma 1, sigma 2, sigma 3. So this is your noise conditional network, and we can have separate for this, for sigma 3 we can have this separate network. But for our computational efficiency, we're just gonna be using a single one. So this is called annealed Langevin dynamics, because we are because we are annealed down the noise level. So if you run this enough, this procedure, you're gonna get the good sample here on the, if I can show you. So this is the sample you're gonna obtain. So and this is the state of the art results on CFR10, and it has FID of better than GAN. So it has a better FID than GAN. So if FID is low, this is better. So if FID is low, so this is 2 point something, 2.2 something. So low is greater, so this is fine. And this is inception score is high, this will gonna go give the, so it is performing good at both these things. So if this is off error, so greater is high, better. So it challenges the long-term dominance of GANs, and it actually giving the very good image generation, high fidelity data images. And you can see some of the images here. So so as we talk about, so how can you train this? So we understand the how can you train this noise conditional score model. So so which score matching loss we're gonna use? So you can use slice score matching loss, and denoising score matching loss. You can use both of these loss. So but for our case, because this denoising score matching will be natural, since the goal is to estimate the score of the Petrov data distribution. So so this is the weighted combination of denoising square matching losses. So this is so from we are having losses from, so this is from I to L. We are moving from I1 to L. I1 to L. So we have we're actually dealing with the L. We're dealing with actually L separate denoiser. We can see a denoiser, or L separate score score function. So you can see here. So for 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 I is equal to 1, so we have the first one, and for the L is equal to 2, we have different loss. I'm just summationing it and taking average. And this lambda sigma I is actually the weighting factor, and this weighting factor determine to which uh, steps we gonna prioritize or less prioritize. So this is gonna go. So for sigma I, if you want to prioritize more or less, so this will gonna go set the importance on how much importance to be given. So this is, so if you solve this, as we can see here, as we have done in deionizing scalar matching, this will actually turn into this, and this will turn into this. So we are no longer estimating the actual score, but we are approximating the approximating the Petrov score right now. So and but we are not for just one noise level, just data plus one noise level, but we are actually approximating the data plus several noise levels from I1 to L, and we are averaging it. And if you solve even more, we're going to obtain this equations. So and the noise, adjacent noise should have sufficient overlap to make the transition across noise scale easily in ALD. For sigma 1, sigma 2, sigma 3, these are the noise scale, means how much noise we're going to add. So for if you add for sigma 1 is the least amount of noise. So if you add some noise, least amount of noise sigma 1, and sigma 2 will must have the sufficient overlap between this sigma 1 and s- there should be some sufficient overlap here. There should be sufficient overlap here, and for sigma 3 there should be a sufficient overlap, so the transition becomes from one noise scale to another noise scale become easier while we are doing Langevin sampling for each different score. So if you are doing ALD, means annealed Langevin dynamics, means we are just annealed downing the noise. Annealed we are just doing we're just annealed downing the noise. So this is the concept, as we are looking for. So how to choose the weighting function. So this lambda of sigma, how can you gonna go choose this thing? So to choose this, as in we gonna consider this as how to choose the weighting functions. So this is our weighting function lambda, and this actually act as this goal of this lambda is balancing different score matching losses in the sum. So how we gonna go balancing it? So in different, so where for the first, so so for this it has for this it will have so this is our sum. So we're gonna go sum of it, sum, and we're gonna go average it, so as written in the formula. So as written in the formula, you can see, so lambda, so it will gonna balance us, and so to which it to which score it will prioritize, the most noisy one or less noisy one, medium noisy one. So it will act as balancing this different score matching losses in the sum. And you can see you can see this is our loss. And what I'm doing here is this is sigma I square, and I'm just sam taking some sample from my data set. I'm taking some sampling, some noise, and this is our loss. And if you do some algebra, this term, front term, will get cancelled from this, and it will get here. So as you can see, and using this property, epsilon theta at sigma can be written as this, sigma I of as theta dot of comma sigma. So if you see, so from I1 to L, so if you just take sample X and sample some noise, and it will act as like this. So this epsilon theta is actually acting as a noise predictor here. So it will acting as a noise predictor. So it will act as noise predictor, and we actually reduce into the tasks of noise predictor. So how we gonna go training this noise conditional score network? For the training, so we're gonna go sample some data from our data set, and we're gonna go sample some noise scale. Means we're gonna how we're gonna sample the noise scale indices from I1 to N. So uniformly for the purpose of, we're gonna use this noise scale to actually, yeah. So this is different noise scale. So we're gonna go sampling from I1 to this level for our training uniformly, and we're gonna sample the mini batches of noise. So we are just sampling Z. This is just a Gaussian noise. If I can show you, this is just we are sampling from this distribution, just Z1, Z2, Zn, and we're going to estimate the weighted mixture of the score matching losses, as I'm showing this formula what we derived earlier here. So if we what we derived earlier, you can see we're just using this formula. We're just using this formula, from and we are just optimize this loss, and we find the optimal theta, so that it will approximate the good theta with as of theta score functions, and we're going to optimize using the SDE, and it is efficient. Then training separate for different noise levels. So if we separately train it, it will take much more computation, and if we just make it this single noise condition network, it will be efficient. So it will take noise level also as additional input. So I am this is your noise condition score network we are passing. So you can have the different for sigma 1, sigma 2, different network also, but we are just making the single noise conditional score network. And right now we are using the discrete noise scale, sigma 1, sigma 2, sigma 3, sigma yal. So we are using discrete. So to make it more efficient, we're gonna go use infinite or continuous noisy scale, so that our sample quality will improve so much. So as you see in number line, so this is 1 and 2, this is 1 and 2. This is discrete, 1, 2 and 3 is in 3. So but if you take this as a continuous scale, it has 1.000.10. So this is infinite. So there in this 2 point, it has infinite number of points. So also if we consider this as a continuous scale, then it will have the different noise levels. So we're going to use the infinite level of noise scale, and it will. So guys, let's understand the concept of infinite noise scale here. So I'm again going to using this slide by Yan Song. So our data distribution is bimodal, as I'm saying. So this is my original data distribution, which has two modes. This is the image of cat. For example, we are taking this image of cat, or this is dog, and we have bimodal distributions. This is our old distribution here, and if you start perturbing it, if you start perturbing with sigma 1 level of noise, this your distributions. So in this region we doesn't have samples, so our square estimation around this region were wrong. So if we add more noise, our samples will also lie within this region. and and if we add even more noise, our sample will spread around all this distribution, and if we even more add noise, our samples will spread all around the region. So this is our data distribution. We don't have a sample here, we doesn't have a sample, a few sample here, and we have a sample all around the space and all around the space, all around the vector field, so our square estimation will be good. So so if we take this as a not just sigma 1, sigma 2, sigma 3, what if you take the continuous time scale as I'm saying, so your score function will look like something like this, as you can see. So if you start adding noise, if you start adding noise, your data will converge into this part. This is only your data will spread all around the space, and this is actually called the diffusion. Or so as you can see here, p of x, this is our data density. So p data of x, this is our original data distributions. And if you start adding noise, more and more noise, you will gonna get this distribution, which is pt of x, and or pi x, which is the distribution in which the samples lies all over the space. But in this region we have less samples, but we have samples, guys. So this concept is called perturbing data with the stochastic processes. So means we take this distribution, we take the sample from the distribution and start adding noise in a stochastic fashion. So we start take this at and we start. So so perturbing data with stochastic processes. So how we gonna go perturb the data using stochastic processes? So we have a clean image and at t is equal to 0. So this is a continuous time scale. So t range between, if I show you, the t range between 0 to capital T. And if I add the t is equal to 0, we will gonna go get the perturb data from this distributions, which is at t is equal to 0. We does not have any perturb, and we doesn't have perturb any data. So as we move forward, we're gonna go started adding noise in a stochastic fashion. So if I show you, so if we have the sample, and if we run this, if I run this process, so this will have. So if I add this process, it will go towards this region, PT of X, which is actually a Gaussian, and and it is actually a noise. So it will make this trajectory here, and it will converge here. So this image will turn into absolute noise. So so here we are using a stochastic process. So this, if we started from here, it will make some trajectory like this, and it will just reach out here.
Of continuous normalizing flows, or neural ODEs, but with very efficient training objectives. And I will cover this
So our time range between t0 to t, and this is a continuous time scale. This is not a discrete time scale, and we're gonna be starting from here, and we're gonna go start adding more and more noise, and it will actually convert into this distribution, which is actually a Gaussian, and our sample will spread all around this space, and our score estimation will be good. But to understand this, so we are gonna go filter up our data using stochastic processes. So I have the samples in my dataset, and I start adding noise. So this is my image in my dataset, and if I start adding noise, so it will make trajectory something like this, and it will gonna go reach into this part, and our my image will turn into completely noisy, and this is iteration is necessary for the estimation of the score in continuous time scale. So xt is the image at the interval between this, and the probability density at time t is can be represented as pt of x, and this t belongs to this range, within this range, and this trajectory is actually can be described by the stochastic differential equation, and this is general form of the stochastic differential equation, and if you it's called this is the deterministic drift of this trajectory and this path, and this is the stochastic part of this processes, and dwt is actually the infinite decimal noise, means we are adding noise as we move forward, and this is the you can just convert this as sigma, so it is not showing here. So you can write d x of t as by use in a simple form, at a 2 SDE you can write this, dx t is equal to sigma t dw. You can write this like this. So sigma t dw we can write it like this. So how can you gonna go generate via reverse stochastic processes? So we're gonna go start from this pt of x, which is our prior, and which are prior, or you can just sample from the Gaussian, and you start generating via reverse stochastic process, and you take a sample and you um, start uh, start removing noise in this fashion. So not removing noise, but you're just doing sampling here. So we're gonna go taking this path, and this is our path trajectory from the pure noise to this distribution in which our dataset lies. So in our case, dataset is the example of painting. So this is our forward SD, which is this defined as dx sigma t dwt, and t is range between 0 to t, and every SD has its corresponding reverse SD, which can be written as this, and this is dependent on the this time dependent square functions, and this is a square function, it dependent square function, and this thing indecimal noise in the reverse in the backward steps. So in the reverse time indecimal noise in the reverse time direction, this is bar you can see here. So it is in the reverse time directions, and this is square functions as you have it. And for the generation, so square based generative modeling via SDE. So forward SD you can return. So we have a data and we have a noise, and we can go from our data. It's the painting, I think. And if you add more noise, your sample will actually turn into this pure Gaussian. And and it has a noise. And if you apply this reverse SD processes, and you need this time dependent square functions, and you can actually go from the pure noise to the data.
Actually recover images from
This is your XT, and you can just go backward, get the sample from this, and this is a time conditional score model, and which depend on theta and time t, and you can actually substitute this things with this thing, and the training objective become like this. So we are sampling time from this time uniformly, and we are putting here, and we are actually calculating this as theta of x t comma t. This is your score matching loss, and this is your positive weighting functions, and how to convert our st into ODE. So this is your ODE ST trajectory, and this is your ODE trajectory, and ODE trajectory does not intersect at all, and the ST trajectory can intersect, and you can convert the
from it.
ODE using the probability.
And importantly, for any perturbation process,
Let's look at how can you convert into ST to ODE. So this is your ST, this is a forward ST, and you can just convert into the probability flow ODE using this equation. So and this is dependent on the score function. So you can just, this is a reverse, this is a corresponding ODE of this ST. So this is dependent on score functions, and let's evaluate. So we have to, if we have to evaluate this p theta of x, and we can evaluate the log probability density of this data. You can using this formula, and this formula involves the integral and the stress, and the stress can be calculated using in computable in polynomial times, and you can estimate this using unbiased estimator, and you can calculate this integral using some ODE solver, and you achieve negative log probability adds better than other models. So I think the fantastic results you can see here, but not good as this transformer. So it challenges the autoregressive models and VAE for the long-term dominance, and it actually helps in this part, which is the probability valuations, in accurate probability valuations and better estimation of data probability.